Okay, so let's do a simple example and exercise on quadratic forms. So you can see this quadratic form. You see that this q equals this value, this representation, and you can see that each term is together to the power of 2. So this is a quadratic form. It can be written like this. So we have a quadratic form. Now what we want in the end is this one. We want to show that there is a constant by which I can say that this quadratic form is less than or equal, not less than or equal to x1 to the power of 2, x to the power of 1, okay, where x1, x2, x3 is like x, y, and z that we started with. So we start by representing this quadratic form by a matrix. You can see that if I enter the 4 to each term, I can divide each one of them by, this is xy over here, this is xz over here, and this is yz over here, because it's 2 plus 2 is 4 for each term. Now to get the quadratic form to a representation as a sum of squares, we will diagonalize this. Now we can't diagonalize this because this is a symmetric matrix, and every symmetric matrix can be unitary diagonalizable. So let's find the eigenvalues. You can see here that we will find the eigenvalues. Here they are, and we found the eigenvalues, and the eigenvalues are this ones. So we can have the diagonalized form. Now for each eigenvalue, we will find the corresponding eigenvectors, and you can see here that we find for eigenvalue lambda equals 4 and etc, etc. Now we found the eigenvalues, which are 4, -2, and -2, right? Because you can see that we have two eigenvalues that are the same. So 4 -2 -2, this is what the quadratic form in sum of squares. So it is less than or equal if I'll put here plus and do here 4 and 4, right? So here we found what we wanted. We found that it's really the quadratic form less than or equal 4 to the power of all of this when you do it plus and plus here.